Good afternoon, everybody, and welcome to my talk, C++ Common Knowledge. My name is Dawid Zalewski, and and that's about it. So you're going to hear about common knowledge items that I think might be important, might be not. I think they're important. Why this talk? I have a hobby, and this hobby is quite uncommon nowadays. I'm reading books, and I especially like reading very old programming books. Like, for example, this one, something that tells you about how the C++ came to being, or this one, a bit more advanced, about the C++ object model, or actually this one. There is a book with the exact title. Somebody already had this idea before. Those books used to be quite common, right? So in the past years, you would go to a blog to read about what's happening in the world. But there used to be times where you could read those books, and that's how you would get your knowledge about everything. The last book here is actually targeted at roughly intermediate audience, but I wouldn't say so. There are very advanced items there. There are very beginners items there. It's a mix of everything, but it's something about, something you should all know about, but sometimes we are not aware of it. And especially if you're coming from different programming languages, or if you're not touching some part of the language, sometimes you might not be aware of it, of some of those. I kind of decided to make a talk like this, but it's a bit different one. So I'm not going to talk about the same stuff that are in the book, and especially I'm going to modernize it a bit. So there are different items, totally different. There are around 100 there. No time here, right, to cover 100 items, much less. And I have a very short program to show you what's going on. This program is really full of bugs. It's like the most buggy one I think I've written ever. It fits on less than A4 and on 2 slides. This is one of the classes there. It's a very prominent class. It's a base class for other classes, just has 2 data members, and a very curiously looking conversion operator. There is another one there, because obviously the first one converts to the named object, so you must have a named object somewhere. Well, that's the named object. Something to admire, right? Just the name inside, and an equality comparator. So operator for comparing itself with another named object. And just because, I know how to program, I added for a good measure also a free function comparison operator that compares to object that piggybacks on the first one. So it's a canonical implementation, right? You just call another comparison operator. Nothing wrong here. You most likely have seen worse. I mean, people write desktop applications in JavaScript, right? So this is not that bad. All this work is not done for nothing. There is something that uses named collection base. That's a named heap. It inherits from it, and it's a heap data structure, so something that makes it easy to pick up the biggest or the smallest number. This actually keeps track of the smallest and the biggest value. So it allocates, or actually it has some data members for it, data max, data min, arrays dynamically allocated, a proper destructor, a proper constructor that constructs everything. And of course, it follows the rule of 5. So it also has a copy assignment, copy constructor, move assignment, move constructor, everything that you want. And then I'm using those 2 classes, or actually 3 classes together. Mostly, I'm going to use the named heap. And that's not much of a usage. I assume there is a function that needs a collection. Passing by a unique pointer, very modern, right? So you can hint polymorphism coming up because I'm passing by a pointer. And I'm using the base class name in the pointer. And there is a heap being created, a copy of a heap being created. Also all unique pointers very nicely. And then I want to pass actually my copy to the function. And because I'm a careful programmer and don't trust myself, I will first compare if those 2 are equal. If it's OK, I call the function needs a collection. Surprisingly, this code compiles. it compiles, it builds, at least if you are compiling with C++ 20 or maybe 23 even, I think you need it for one feature. And it builds without any errors. There are not that many warnings also triggered, and you might miss them. Not very important warnings. Clang and GCC show you 2 warnings. MSVC shows 1, and that's all. The program, unfortunately, I think crashes or runs forever, or something like this, despite not being compiled and despite being very short. If you apply your common knowledge and common sense to what you've done or what I've done, there are more than 10 violations, very big violations of things you shouldn't be doing at all whatsoever. And if you're a bit familiar with C++ and about what C++ is about, you should have picked up all of them. Or not all of them is maybe too much, but at least 5 of them. There are more than 10. And in particular, what I've been doing is not initializing data members, triggering undefined behavior multiple times, allowing implicit conversions, which is not that great, right? Confusing assignment with initialization, violating one definition rule a little, not that much, totally neglecting array II and exception safety. Leaking memory, I was leaking memory, believe me or not, I was doing it. I was totally ignoring cons rules. Triggering infinite recursion on the way, that's there on the slide. Slicing objects and making name lookup cry, totally cry. So let's try to fix those. And fixing is quite easy. I'm just going to walk through, in total, 12 different items that are not intended to be read now, that are why they are mangled. Which will help us fix the program. And we're going to go from the simplest rules to the most, I wouldn't say difficult, because we are still somewhere in the beginner's intermediate level of C++, but things that will help us figure out what's going wrong, what's wrong, and hopefully will help you figuring out this kind of errors. If not in your code, then sometimes maybe if checking beginner's code, which you are reviewing when you hire new colleagues, for example. The first one, a very common one, uninitialize means indeterminate, right? We all know it. In C++, you have to initialize everything because the compiler is not so nice. I was actually triggering undefined behavior, not like this, but I was triggering it in a similar way. You see, the named collection base is doing something totally awful. It has 2 data members, that's great, but it also has a constructor. It's a user-provided constructor. It doesn't do anything, right? It doesn't initialize anything. And that's already like code smell, because it means that the name will be properly initialized. The compiler will call the default constructor for the standard string, but unfortunately the size will stay uninitialized. Its value is indeterminate. Reading it is undefined behavior, formally. If you get rid of this ugly constructor, everything will be fine. Now our class becomes an aggregate. And because we have braces when we initialize the NCB, everything is good. No problems whatsoever. If you skip the braces, again, undefined behavior. That's something that might be surprising, but that's how aggregates are initialized. The lesson, keep the braces around somewhere. And the best way, of course, or the best place to put the braces is directly in the class with the so-called in-class member initializers, right? If you do it, if you even put some initialization there, you're good to go. There is no undefined behavior triggered whatsoever, whatever you do. So it's a better way of doing things. Let's do it. Item number 2. Declaration order is initialization order, a very, very, very common error, especially if you are beginning with C++. I've done it also. I committed the same crime on the slides. And I think the crime is now pretty obvious when you look at it, right? So what I intended to do is, of course, to have 3 data members, data min, data max, and the capacity. That's my declaration order. And I was hoping for the different initialization order. Like in my constructor, I first initialize capacity, and then I'm using the capacity to allocate to arrays. Unfortunately, that's not what happens, right? declaration order is initialization order, especially when it comes to classes, or only when it comes to classes. Actually, when it comes to everything, right? So in whatever order I declare the members in my class, in the same order, they will be initialized. It doesn't matter what you write. The compiler is smarter than you, which pretty much means that at the stage when I'm initializing data min and data max, those two are actually the capacity has an indeterminate value. I'm reading something value that doesn't exist. I know nothing bad will most likely happen, right? Because very likely there is a 0 there if you are lucky, but it could be that you are allocating a couple of gigabytes, and that might not go that well. Your hard disk most likely won't get formatted, contrary to what people tell you about undefined behavior, right? So don't worry about it. Nevertheless, it's bad. A simple fix, put your data members in the right order, and then everything is fine. Which brings us almost to the next item, right? This is fixed. We are done. Or not to the next item, to the application of the first item. When we initialize data members, why even initialize them in the constructor when the initializer is fixed to 16 in this case? Just put it there in the initializer list, directly in the list of the members, and you are done. This will be fine, whatever you do. Now, unless, of course, you mix the order. The next one, assignment is not initialization. Two things that are very often mixed, right? And people, especially coming from different languages, tend to put assignment where the initialization should happen. We have even special syntax for initialization nowadays, the curly braces, right? Sometimes it looks very ugly, but in the constructors, it doesn't. What you've seen on the slide, on the first slide, or on the second slide, it was the second slide, let's say, was something like this, and it's still there. What I'm doing here is, of course, my named heap is inheriting from the named collection base, so obviously it must initialize the data members of the named collection base, right? So it has to initialize the names and the size, and for the simplicity, I'm just initializing the name here. I'm doing it in the body of the constructor, but that's not really the place to do it, right? That's actually the body should be totally empty, like most of the cases, maybe some logging statements, something like this. Those of you who've been programming a lot know that all the initialization happens in a different place, particularly here. So even if you don't mention anything there, even if you don't initialize your members or your base classes in the member initializer list, the compiler will do it for you. It will just sneakily call the default constructor for a class, or in our case, it will initialize the aggregate, the named collection base, by calling there is no default constructor for an aggregate, but let's say a default constructor, right? That's a bit wasteful. We are first initializing and then overwriting those values, again, in the body of the constructor. So first, for example, the constructor of the standard string will trigger in the default constructor, and then we are overwriting this value. Why do it at all? If the compiler can do it, we can also do it. Just put it there where it belongs to, using the aggregate initialization syntax. This has the benefit that the size will be initialized to 0 also, without explicitly mentioning it. And we are kind of good to go. So assignment is not initialization. Item number 4, implicit conversions are almost always evil. You shouldn't do them. I've done it twice on the slides with the program. The first one was quite obvious, and it didn't trigger any nasty behavior, actually. So I have a constructor, the named heap, which takes a standard string. It's the so-called converting constructor, right? It converts from one type to another. And it does it, there is no harm, you might think, and I agree. You can write, silly code like this. There is no harm in it. It's just to confuse your beginning colleagues, maybe. It will compile just fine. Doesn't make any sense, but you can do it. Where the harm really comes into play is situations like this. Imagine you have like a function, crunch the numbers intensively, something you are likely to see in many code bases, and it takes a named heap of double by constant reference. Well, now you can call this function with something like this, 1 little, 2 little, or no, 1 medium and 1 big number. It will compile just fine, right? Doesn't make any sense whatsoever. Might be used as a practical joke. It's a good joke, I would say, even. It won't do anything because this heap is empty that you are passing to the function, but nevertheless, it shouldn't happen. Disable it. Just don't allow something that's stupid. Sometimes converting constructors makes sense, but here, absolutely not. Why would you convert from a string into the heap? Make this constructor explicit, and you're done. The conversion becomes impossible, at least implicit conversion. There's another case of the same thing, and that's this one. Look at it. I'm comparing two heaps, or actually I'm comparing two pointers to the named collection base. And that's quite weird, because if you remember, then the named heap cannot be compared. There was no comparison for it. The named collection base actually also cannot be compared, but it has this operator inside that converts it implicitly to the named object. And the named object can be compared, right? We had the operator, equality, comparison implemented, so named objects can be compared. And just because of this whole chain of events, we now can compare two named collection based. Or for that matter, even the named heaps. Doesn't make much sense, right? I mean, most likely two heaps are not equal when their names are the same. That's not really the case. Disable it. Disable it by marking something like this explicit. I'm saying it should be explicit, but you will be seeing it again without the explicit when we are talking about a different item. Item number 5, everything needs to be defined just once. It's about the one definition rule, something that scares people, and it should, because it's very, very difficult lingo in my opinion. But the concept is very simple. My code, I mean, looks good now, right? I already applied at least 2 different refactoring to it to fix many problems, but it's still not really as it should be. Specifically, I have a magic number there, at least in this version of code. And this magic number shouldn't be there. I should name this constant. I should name this number somehow, so it's easy to track, so it's easy to reason about it. So let's put it outside. And that's actually what also I had in the beginning slides. It was put outside. Now, the problem with this is that such a piece of code usually lives in a header, right? And you already can smell the disaster coming when you include this file multiple times. This is something like a named heap, looks like something that's going to be used a lot around our code base. So imagine this scenario, a very simple scenario. We have the named heap with the definition of a variable there in the global scope, and we have 2 different source files. The number cruncher, where the function crunch numbers intensively comes from, and the stats printer. Both of them include the header, both of them are compiled, produce object files, and then the linker comes in, and the linker says no. The linker will tell you that you have a multiple definition of the same object. Especially, it will complain about the k cap being defined twice, at least. It's usually a very ugly error. It starts with LD, and that's how you recognize it if you are on Linux. And then you have to start looking where it is. There is a rule in C++ that says that everything needs to be defined once, and only once, in any of the, or not, among all the translations units that are put together by the linker. So if you have multiple translation units, and in this case we do have, source files are usually known as translation units, and the same name is defined twice in different translation units, you are cooked. The rule only applies to variables and functions, nothing much more, and things that are not inline. So you can mark it inline, like for example, or your members of a class are automatically marked inline, and you don't have this problem. This is not inline. Solutions, very easy. Either make it like a const x per something or a static something, and the problem is solved, like it's not a variable anymore, or make it inline. Nowadays, we have this pleasure of applying inline to the variables. It has a very curious effect. The linker now will accept multiple definitions of the same symbol, but you have to promise that they're the same. The linker doesn't check it. You can make very nice practical jokes with it, so, but you shouldn't. And if we are actually talking about it, why just not put it, inside the class? It's by default now inlined, whether it's const x per static or not, and the problem is solved anyway. Item number 6, only fully constructed objects benefit from RAII, so resource acquisition is initialization. The very ugly, name, not ugly, but something that's very hard to explain, right, to people, for something very simple. Can you spot the problem here? I'm pretty sure you can. Some of you can spot the problem here. And the problem is I'm actually having 2 resources, and I'm allocating those resources. Let's simplify this class a little. So those are my resources, right? Remove everything that's not needed. And now we have just 2 dynamic arrays. And let's have the happy scenario. We're calling the constructor. In the process of calling the constructor, the data min is allocated on the heap. Everything goes fine. And now the data max is, it's not allocated. We get the std_alloc error. Something very unlikely to happen, but generally speaking, errors do happen in the construction. Not std_alloc maybe, but something else. On the other hand, you might be on an embedded system, a resource-limited system, and std_alloc will happen. Now, the big question is, what happens now? We just allocated a resource, right? We just allocated a piece of memory on the heap. We have to free it, but we have an exception in the constructor. So the million-dollar question is, does this delete ever get called, right? And the answer is no. This delete won't ever be called because there is a rule, and that's actually what RAII is about, that the destructor is guaranteed to be called for every fully constructed object. This is RAII distilled to the basics. Now, what is a fully constructed object, right? Because that's another question. A fully constructed object is an object for which at least one constructor fully finished. This is not the case in our scenario. You might try to be smart. I also tried to be smart many times before I knew better and do things like very exotic things like this one, like function try block. These things exist. You can rob the whole function in a try catch block. Also the constructor, and hope this will work, right? No, it won't. It won't because, first of all, it's illegal to refer to any data members in the catch block of the constructor. You just cannot do it. It's undefined behavior, like plain blank. And secondly, even if you could, what's the value of data max now? Assuming the data max through. It's indeterminate, right? You don't know. It might be null. If you're lucky, it might be something else. So you might call delete on a pointer that's not really pointing to something for data max. So it's dangerous even to do it. You don't want to do it. And anyway, you will get the exception because the exception will be rethrown by the runtime. What's the solution to the problem? Well, the solution is actually quite easy. If you look at it and apply the rules that the destructor is called for every fully constructed object, you might come up with something like this. Let's make a default constructor that does absolutely nothing. It will actually use the default initializers that initialize datamin and datamax to null pointers, and let's delegate the job to it in our real constructor. And this will magically work, actually. This works because, you know, the default constructor will not throw, it does nothing. And once it's called, the object is fully constructed. You benefit from the destructor, and the destruct will do its job because only the objects that allocated something will be non-null. But it's ugly. And you shouldn't do it because, for example, it breaks the rule that I mentioned before, that initialization is not assignment. I am now doing exactly this, right? So you shouldn't be doing it. And if you look very closely at it, you might realize after some time that actually, if you get rid of one of those data members like this, you don't need any special handling anymore, right? Because if datamin allocates, everything is good now, the destructor is called and you're good to go. If it doesn't allocate, well, who cares? The destructor doesn't have to be called also. We don't care. This might lead you to another item, that what RAII really means is one class, one resource, especially one class, one dynamic resource. This is what RAII stands for. And with this one, you might come up with something like this, right? But now we are in this ugly situation that we lost a data piece. So of course we abstract away directly and create a type like dynamic memory that keeps around just an array and the size of this array, which pretty much is a kind of a vector, right? But okay. And then put it in our class instead of what we had before. Quickly realizing we don't need any destructor whatsoever because everything is taken care of automatically by the runtime now. And if we are at least with C++11, we quickly should realize that this is what unique pointer is for, right? Or state vector for, and not your manual memory management. Which brings us to a totally different item. Item number 8. Member functions have an extra this parameter or an extra this argument passed to them. It's a very profound item that really goes into the object model of C++ and how things happen in C++ that helps you understanding how more advanced feature works, like deducing this that has been kind of there in the language now, right? And you can use it. We're coming back to the base, to the name object, because this is where really a lot of bad things are happening. Right, this named object overloads the inequality comparison. So the operator not equals to with another named object. And you might think that when the compiler sees such a function, what it does, it kind of looks at it like this. But this is not true. What the compiler truly sees is more something like what you see on the slide. So there is a function, operator not equal to, that takes 2 parameters instead of 1. And the first one is the implicitly injected, or implicitly, injected is a good word here, pointer to the current instance, named this, and that's pretty much all. It's there. It's always there. If you don't believe me, go to the assembly, look at what the assembly is generated. It's always there, unless it's optimized away, of course, because sometimes it is optimized away. But it is there. This pointer exists. Why does it matter? Why is it important? Well, it's important because I'm making very grave mistakes, partially because I don't understand how this relationship works. I have a member function, and as I mentioned before, there is also a free function which piggybacks on the member function. It's a canonical implementation. Yeah, that's how you should do it. Actually, you should have one function, one should call the other, negating the other. That's how it's done. And then imagine, of course, after inlining it, because you know that things like this should be inlined, that I'm creating 2 named objects and comparing them against each other. If Alice is equal to Bob, great. Our chain call looks like this. First, we compare those two. Then, obviously, because it's equals, then we call the free function operator, which in turn, because it's internally calls not equal to, will go here, right? I mean, that's what we are hoping for. Unfortunately, that's not really what happens, right? Depending on which compiler you are, on which language version you are either not compiling this code at all, or you are getting an infinite recursion here. And I think the first solution is much better, actually. It's much better to have a compilation error than just getting stuck somewhere without any clear reason. Why the infinite recursion? Well, look at this. What I'm doing there is comparing in the implementation of the equals operator. I am comparing two things. So we already know that what the compiler truly does is something like this. It calls the member function, or it tries to call the member function. It seeks to call the member function that's implemented inside the named object, and it rewrites it to match the parameters into something like operator not equal to address of A, comma B. So it's trying to match the parameters, right? Remember that there is the first implicit argument to this operator is the pointer. Then it comes up with the types for those. And what it comes up with is that the address of A is a pointer to the const named object, and B is just reference to the const named object, right? And it's const in both cases because we qualify both A and B with const. So there are const objects. There is no other way. And unfortunately, this doesn't match our operator. Our operator is not const. The first implicit pointer is not const, so the compiler will say no. I'm not going to call your member function, and since I am on C++20, I'm going to apply a very cool rewriting rules that I am able to apply nowadays. What are the rewriting rules? Basically, since C++20, whenever a compiler says equals equals or not equals to, and it cannot find a matching function, it is allowed to rewrite the expression into the opposite expression and negate it. So basically, it cannot find not equals to here, so it is allowed to rewrite the expression into something like this. Great, we have a full match, right? Now we know what's been called, and that's why the infinite recursion. We are calling ourselves infinitely in the loop, and actually that's one of the warnings that GCC and Clang trigger. The other one was the mismatch in the ordering of the constructor and the declaration of the arguments of the members. But this one is something that Clang and GCC will warn you about. And you might scratch your head then, very often, because you don't see the recursion, but it's there. Be careful about it. How to fix it? Well, you just have to understand the second rule of playing with this, that const member functions have const this parameter, right? This is what we have, right? This is what the compiler now sees when it looks at the not equals to operator. This is what we want to have. A very easy things to achieve. Just put the const keyword after the member function and you're done. This function does qualify this const does qualify the this pointer. It's really confusing with this all the time, I know. But nevertheless, this is what truly gets qualified. That this pointer that's implicitly passed to the member function. And now everything is okay. Our chain call is as it should be. So we are calling from the bottom one to the inline operator equals equals, and this one in turns will call the last one, the inequality comparison, and everything goes as expected. Is there something we can fix about this code? I mean, now that we know about the rewriting rules and we are anyway compiling for C++20, I think there is plenty of opportunities to fix this code. Like, if you know that the compiler anyway synthesizes the other one, why would you write two of them? Like, one is enough. The compiler will make the other one anyway. So let's do it. And with that one, let's introduce another, a bit more advanced item. And especially, I think, if you are in writing sometimes codes that's used by somebody else, that should be known to you. Otherwise, you might be surprised about it or might not know about it. Hidden friends are here to help you. So, as I already said, it doesn't make much sense to write both comparison operators or equality operators. It's just enough to have one of them, because the compiler will make or create the other one. So far, so good, right? And for the sake of the argument, let's say that this code works, because it should work now, and it compiles. But this still works, because for some reasons, and sometimes you have those reasons, we couldn't make the conversion from the named collection base to the named object explicit. So you still get implicit conversion, and you still can compare to objects of the named collection base. And we know it shouldn't, right? It's a bad thing. What are your options there? There is an option, and the option actually is in the title of the slide. It's a hidden friend. It's a not so well-known idiom, but it's a very good idiom. It's for hiding functions from the lookup. So if you don't want a certain function to be automatically to be found by the lookup when the compiler tries to find a match for your call, specifically if you only want it to be found where at least one of the arguments totally matches the argument or the parameter in your function, just move those function, inside the object that it's, concerns. In this case, our bool operator can be moved into the named object. And it won't work, obviously, because now it has 3 arguments, and it should have only 2. It has 3 because there is an implicit this. So you make it a friend function and declare it or define it directly inside the class. A friend function that's defined in place is called a hidden friend. It has very special magic properties. It won't be found or used for that matter if at least one of the arguments that you try to call this function with doesn't explicitly match the one that you list there. So if it's, I cannot point. Oh, I can point. No, I cannot point. I can point. If it's not the named object, right? In our case, it's not. The named collection base is not a named object. So it won't be found anymore, this comparison operator, by the lookup. It's impossible. It's hidden. This function is now only found. Okay, doesn't matter. Let's not talk about it. So this won't work, and that's great, right? As it should be. It shouldn't compile. And if we are already talking about it, and about hidden friends, and about how to declare functions, how to declare or define operators, comparison operators, and so on. And we are in the modern language. Why not just go a step further and do something like this, right? Just default it, declare it as a friend, and it's going to do everything you want. It's still a hidden friend, but now you have all the other comparisons synthesized for you out of the box, so you don't have to do anything else. So that was a hidden friend idiom, a very powerful thing for hiding your functions from the lookup. The next one. Polymorphic classes need virtual destructors. That's where I leaked memory. You didn't most likely see it, but I did leak memory a lot in the first slides. I had something like this, or actually I didn't have something like this. It will come, but let's look at those couple of examples. What do they have in common? I'm creating like a pointer, a unique pointer to the named collection base and initializing with a named heap. Or I'm doing something different, like I'm creating again an object on the heap of the type named heap and assigning it to the base pointer, base class pointer, and deleting then. Or doing something like this, it's a bit more hidden now. I'm creating again an object on the heap, named heap on the heap. That's unintentional. And then I'm calling a function with it. The function that takes a pointer to the named collection base. All of this have something in common, right? You expect somewhere at the end of the lifetime, when the named heap is not needed anymore, that there will be a delete call on the pointer. And it will be, of course, the unique pointer will do it for you. And for the middle example, we just did it explicitly. So we expect something like this to happen. And what we want it to do is, of course, to call the destructor of the named heap and then the operator delete to free the memory, deallocate the memory. But that's not really what happens, right? That's not what happens because we made a huge mistake. And I was actually quite surprised that neither compiler warned about it, because they sometimes do warn about it. This time it didn't. This is our named heap, right? It doesn't have a destructor because it doesn't need it. Great. This is our named collection base. It doesn't have a destructor because it doesn't need it, except it does. It does because we intended to use it in polymorphic code, a code where the child class will be referred through the base class pointer, and what's even worse, destroyed through it. So what truly happens, because we don't have a virtual destructor here defined, is that when the delete PTR is called, the destructor of the named collection base is invoked and not of the named heap. This is not what we want, right? Because it means that we are totally leaking memory. Shouldn't happen. Is there a fix? Of course there is a fix, and it's a very easy fix. Just put the virtual destructor there, default it, and you're done. It becomes a class that can be used polymorphically, and whatever we do with it now, it's going to be good, it's going to work as it should. So this was kind of an example when things can go wrong when dealing with inheritance, right? A basic example, which you are not likely to do unless your code base is very big and unless your compiler doesn't warn you about it, like it didn't me. The next one is in a similar spirit. So we are going to talk about object slicing, or about copying child classes or derived classes when referring to them through the base class. Not a pointer, but just through the base class. And this is something that, it's, in my opinion, it's sometimes very easy to see. Like, for example, on this slide, in these 4 lines of code, I'm slicing an object. And in particular, I'm slicing the named heap. And by slicing, I mean that I created a heap, a named heap that owns 2 different arrays, and then I make a copy of it, but I'm only making a copy of a piece of the heap. So I'm only making a copy of the heap that belongs also to the named collection base. I totally neglect the heapy part, let's say. It's not really visible here, right? Because it's kind of hidden in this, make unique named collection base everywhere, dereference. But what really happens inside is that the constructor of the named collection base will be called, and the reference to the heap will be passed to it, which is totally legal, right? And the named collection base will be created without the heap part. It's more obvious when you do something like that. So when you just have a function that takes, like in this case, a named collection base by copy, you can already see that there is a copy being made. It's clear. The consequences are always the same, right? So the consequences are always the same. Basically, we are doing what's called object slicing, which means that we are not copying the whole object, but only a part of it. In this case, we are copying the name and the size, and that's all. That might come as a surprise later on when you will try, for example, to do some casting of this heap, of this copy of the heap that you made. Nasty crashes, no compiler warns about it really, and that's sad. An easy fix, of course, like for that one, I mean, okay, it's not an easy fix, it's an ugly fix, but the fix exists. Just pick up the right class when making a copy, when using unique pointers. Much easier fix when you're passing to functions. Instead of passing by copy, just pass by reference, like maybe a const reference, and you will be good. No harm will be ever done, right? No object slicing. And with that one, we actually reached the end of the list of all the 12 knowledge items. Those are there. All mistakes were truly made on the first 2-3 slides. I managed to do all of them, luckily. Try it for yourself if you want. See if you don't believe me. Are there any questions? So thank you very much. I don't know. I have one.
Yeah, I'm just going to ask a question from the online audience. So this is a question from Peter von Niederhausen. In issue number 10, when do we have to explicitly define equal equals if we ask for the rocket operator? Or sorry, spaceship operator.
I didn't understand the question. No, you can repeat it, of course, but that's me. It's not.
Okay, let me ask it slowly. In issue number 10,
yeah.
When do we have to explicitly define the equal equals operator if we ask for the spaceship operator? I presume we have the spaceship operator, and she wants to know, is there any case when you can also define the equal equals?
I wouldn't say so. Why would you do it then? I mean, if you have the spaceship operator, it covers all the bases. So, if it was the question, of course. Yeah. So no, you don't need to do it anymore. I don't think so, unless you want to confuse some people, right? I mean, you might do it. I think you might do it because you might hide, for example, the spaceship using the hidden friend and explicitly define the equals outside, so it's visible to the name lookup, right? So you can distinguish between the operators. But yeah, is it a good design then? I don't know. I doubt it. Yeah.
So my question is also about the equals operators and stuff. I can't remember which slide it was at the kind of start of the speech, but you said that the compiler could convert, or like decide to convert from not all in equals operator to the equality operator instead. Do you know what I'm talking about right now?
Yes, of course.
That's kind of scary to me. And I wanted to know, do you know of any more of these like implicit conversions or whatever you're supposed to call them?
That's the rule that has been introduced just. I don't remember in C++ 20 or 23. It always happens. A compiler is allowed to rewrite one comparison into another when one is lacking. That's all.
Do you know of any other operators or other special functions that behave this way?
No, luckily not. Okay. I don't think it's scary.
I mean, maybe like the less than operator could be converted to like larger than or equals to.
Remember that you can always explicitly disable other things, right? If you don't want the conversion to happen, no, you cannot disable it. Yeah, you could delete it. Yeah, just delete the other one, but that doesn't help you here.
That's kind of scary to me. But thank you.
So you cannot delete it. No. I was hoping the same, but no, we cannot. because then you delete yourself. I mean, you have to delete that one to disable this. This is what it's rewritten to, right? So it's rewritten into the same operator. So how do you delete this particular use case? I could imagine that there is a way to do it, but I don't want to do it.
Okay, I have a question about item number 5. Are you aware of any best practices regarding adding the inline to your const expression variables? Because adding the inline will make it more consistent because everybody sees the same address of your global constant. But on the other hand, these types of constants, I don't want anyone to access the address anyway. So I often find myself struggling. Should I add the inline, shouldn't I? Because it always suggests not what I want to do. Because I don't want you to access the address, but if you do, I would want it to be consistent.
I mean, I understand your question, I think, but inline has a very specific reason. I mean, reason for existence now in C++, right? Inline means literally allow multiple definitions or redefinitions. As you say, there will be only one object created at the end, but that's part of the linker job, right?
But if you declare it inline, but if I don't declare the const expression variable inline, it will have internal linkage, and it will be fine in terms of the one definition rule, yeah. But everyone will see a different address, and
yes.
That's weird. And but I don't want them to access the address anyway, so to rely on that.
Then just do it. Make it inline.
Okay.
If you don't want them.
Okay.
Or hide it.
And another comment, if you explicitly define the spaceship operator and don't default it, you have to explicitly default the equals operator to make it available. That was maybe the other first question.
Thank you. And that's really funny because I didn't have to do it. And it compiled.
It compiled because you defaulted the spaceship operator.
Yeah,
but if you have to implement it in terms of
I understand
maybe delegate to... okay.
I have a further comment from Peter online, and I think he might be agreeing with our previous
Now
commenter.
I understand the question.
To clarify, he says, you do not get the equals operator for free in some situations, even if you ask for the spaceship operator. So that's... okay, and I have another question from somebody online. Roman asks, you were talking about memory allocation issues. Are there any techniques to handle bad allocs?
I think crash the program. I mean, if you're out of memory, that's the end of life of your program anyway, right? Unless you can switch to a different allocator or something like this. I mean, that's what I've been told always. So it's a disastrous situation, right, when you're out of memory. So your options are very limited at that moment. Unless you're on some heterogeneous system and you don't care, you have multiple memories or different allocators maybe, or you don't know, or you maybe had a very bad allocator that just one had kilobyte, and then it's okay.
I seem to remember writing code decades ago, which would, at startup, would allocate, would reserve 2K or something like that, and then if it got a bad alloc, it would the normal allocator would switch to using that 2K for the last get me out of here cleanly. So
yeah, we sometimes tell beginners to try it nowadays, to especially on Linux, to just allocate as much as possible. It's an endless story. You can allocate, allocate, and allocate, you know, and it never stops. It's a virtual memory. So, are there any more questions? If not, thank you very much for attending the talk and for the questions. And see you around.